Good morning, mathematicians. It's ASMR coffee time. My friend just sent me a cool paper this morning, so I'm gonna show you guys that first. Also, I mean, I'll try to remember to say this later because there's probably not too many people here yet, but video unavailable. My friend just sent me a cool paper this morning. Oh, there we go. Tomorrow there won't be office hours because I'll be out hiking the mountains. People here yet, but video unavailable. Wow, things are seeming slow and laggy today. It's freezing up. So, what's all that about? Oh, I hope the stream isn't gonna crash. Hello. New geometric Langlands drop go crazy. Indeed. Yeah. Maybe we could take a look at that paper too. Again. Hello, Black. Hello. Okay. I've got myself organized here. Yeah, let's take a look. So, this is based off of, a friend of mine. We're discussing some ideas related to some of his research and talking about representation theory and stuff. And he ended up sending me this paper. Oh, Thunderhead Bay. Thunder Bay, Canada. Nice. I've never even heard of Lakehead University. But this is a really cool paper. Just a nice short little paper with some like classic group theory. Let F be an algebraically closed field characteristic other than 2. We classify finite groups for which every irreducible F representation is of degree 1 or 2, and the degree 2 representations are star stable. So star, I believe that means you basically compose with, instead of taking your, like if your representation's pi g, you go pi of g inverse and you take the transpose of that. So it's like a contragradient, not contragradient, but like a whatever dual type thing. Yeah. And I just think this is such a cool paper. I feel like this is stuff I want to do. I want to write a paper like this. Yeah. So the main result, yeah. So here's the main result. This is really cool. So also immediately I'm like, well, what's going on in characteristic 2? Where does the proof break? What's the workaround? That sounds interesting. So let G be a finite group and suppose that F is an algebraically closed field of characteristic P greater than 2. Then all irreducible F representations are of degree 1 and 2. And all of the representations are of degree 1 or 2 if and only if G has a normal CeLO P subgroup P where G mod P is abelian. G mod P has an abelian subgroup of index 2, or G mod P mod the center of G mod P is this triple product. This is so cool. I mean, I don't know. I just love these kinds of theorems. Because I believe that there's a theorem, for example, that says, if you have, so of course, all the representations of a abelian group are one-dimensional. All the irreducible representations are one-dimensional. And I believe we know the converse as well. So that says that if you had a group and you somehow knew, without knowing that it was abelian, but you knew somehow that your group, all of the representations were one-dimensional, then that group would be abelian. Yeah. Which I guess this is a special case. Like, that's a special case of this, right? Because all of the irreducible F representations are of degree 1 or 2 of your abelian group. It's just they're all of degree 1, but they are of degree 1 or 2. So this is like a generalization of that result, which I think is really cool. And then they also have theorem 2 here, kind of a similar sort of thing. So if F is algebraically closed and G is finite, then the irreducible representations have degree at most 2. Be any finite group. Right. Okay. They're degree at most 2, and the two the degree 2 representations are star stable if and only if the field is characteristic 0. Interesting. And G is abelian. G contains or G contains an abelian subgroup of index 2. And for everything outside of that abelian subgroup, we have this conjugation relation. Or G contains a subgroup of index 2 and is an elementary abelian 2 group, or the center of G is an elementary abelian 2 group of index 4. Okay, that's all in subcase 1 in the characteristic 0 case. And then in the characteristic P case, you can say that it's an if and only if with G having a normal P CLO subgroup and G mod P is one of the types in part A. Very interesting. Very, very interesting result, in my opinion. I don't know. So I don't know, maybe we should just go through the paper. Look at some of the things that go into it. Like there's definitely some like classic pure group theory. G be a finite group such at degree 1 or 2. Assume that G is not a P group and let Q be the smallest prime other than P. Which divides G. Then G has a normal Q complement. How's my day been? Good so far, but it's just started, so that's not saying a lot. I don't expect it to make a south turn dramatically or anything. But yeah, good so far. I guess it's a good day to do some laundry. That's what it is. Actually, it's not a good day to do laundry. It's kind of nice outside. Actually, it looks nice outside, but it's kind of windy, so maybe it is a good day to do laundry. Either way, laundry and math. Those go together well, right? Because you have to sit and wait to do your laundry for a long time. And that gives you lots of time to do math. Hello, Daysen. Hello, Daysen. Wait, I have to think about what does that converge to? I mean, wait, does it converge? If the absolute value of high is less than 1, then It should converge, right? Yeah. Oh, and we're pulling in, I mean, this makes sense, pulling in Brouwer characters because we're doing mod P representation theory. The result of this discussion is that if F is algebraically closed and contains no elements of order characteristic F, then the irreducible F characters are in one-to-one correspondence. Right. And it preserves the degrees of characters, right? If F is an algebraically closed field, Oh, they're pulling in theorems from other place. What is the center of a group? The center is the subgroup of all elements that commute with the everything else in the group. Oh yeah, maybe I should finish doing. Maybe I should try and vindicate myself with this like basic geometry problem I couldn't solve yesterday. Oh my god. The center of a group is the set of all elements such that G such that so it's all elements Z such that for every other element G, ZG is ZG, so that it commutes. It's the stuff that commutes with everything in the group. So it is abelian, and it is normal. And the center of a group is the entire group, if and only if G itself is abelian. So, for example, the center of the group of n by n matrices over your favorite field, let's call it, I was about to say something silly. No, I think this is true over any field. Yeah, is going to be the set of will be the collection of just diagonal matrices where you have the same entry along the diagonal, and X ranges over the non-zero elements of your field. So is every matrices under multiplication? Yes, matrix multiplication is associative. Yeah, certainly over a field. If you have matrices over any field, definitely matrices over any ring, matrix multiplication will still be associative. What about non-commutative rings? Because something goes weird, I think, when you start doing non-commutative stuff. No, that's not true. I think you can do matrices over non-commutative rings because, like, I did matrices in differential forms, and those aren't commutative. But maybe you lose associativity there. I don't remember. Although I think, yeah, I don't remember where the. I mean, maybe we should just try and go back to the proof that matrix multiplication is associative and see what we end up using. I think we only use associativity. I think as long as the underlying structure is associative. I think that's all we use in the proof. Matrices of morphisms In any abelian category. Multiply matrices of morphisms. And what do you mean by a matrix of morphisms, Arad? Like, are we assuming that this is like a locally small abelian category, and then we can take an equivalence into modules and then treat things element-wise or something? But then, wait, how do we even make a matrix? Yeah, I don't know. Is there... where do I read about matrices of morphisms in an abelian category? Also, that reminds me. Sorry, I know there's a bunch going on in chat. I'll address in a second. But that reminds me that one thing that I wonder, which would take me like 5 seconds of Googling to probably just absolve my curiosity, is, so, if you've seen my video on the, large cardinals, you know that I believe, and now that you should believe, in an infinite hierarchy of large cardinals. But then I'm just curious about how this affects like smallness results, right? Like, so there's results about like, oh, suppose you're I don't know, like there's some result that like says assume that your category is like locally small, right? Meaning your Hom sets are small. But then do all of these, like, can you immediately bump up each one of these results to being like, oh, I'll assume that it's kappa n small, and then say something. Mr. L, the large cardinals, what's a good definition to take? I mean, you could say a large cardinal, or an inaccessible cardinal would maybe be a better way to say it. Okay, there's some other fancy ways to say it. Basically, the nicest one I've seen is that kappa is like large or inaccessible. There's a more technical way to say this, but basically, if it is a model of ZFC. So, for example, it would be for example, that you can't form the set of all sets, right? But one could hypothesize the existence of a cardinal kappa where all of the sets do, where it's sort of large enough that like all ZFC sets fit inside of there. So it itself is sort of like outside of ZFC. So you can hypothesize the existence of a set that contains all of the ZFC sets. But it itself, of course, is then like outside of the model. It's like an extension of our universe. So it's like taking the ordinary universe of mathematics and then extending it by hypothesizing like yet another larger set that goes beyond everything. Okay, let me go back up here. You're watching some high school geometry and you thought of something. What if we create a course where we create a space of polygons satisfying geometric conditions, and then we can ask, what is the continuous deformations satisfying such conditions? A space of polygons satisfying certain geometric conditions. Oh, okay, and you say, for instance, down below. For instance, the following Pitot, I don't know who that is. We can start with all quadrilaterals satisfying circle inscriptions. Okay. I mean, I think there are studies out there of isn't there like a classic version in some of these documents explaining so you can find some PDFs talking about what a stack is, and they talk about like the stack of triangles, something like that. You can actually multiply matrices of oh, right. Yeah, I was asking about that question before. Okay, right. A morphism between direct sums is equivalent to a 2x2 matrix of morphisms. Oh, yes, I see. Right. Okay, I get what you're saying. Yes. Okay. I'm with you now. Associativity of matrices only depends on the commutativity of the plus. Yes, commutativity of the plus, but also I think the associativity of the multiplication of the underlying thing, right? Like, okay, maybe I should write it out, but like if you think about the proof, like think about how the proof would go from the definition with matrix multiplication. You definitely need that. Or for example, I mean, just look at the diagonal matrices in GLN. Like if you didn't have associativity of the underlying algebraic structure ring or whatever, then your diagonal matrices already aren't going to associate. Could you associate the center of a group to a convergent subspace of a phase plane? Well, I mean, probably not. As soon as you say the word convergent, probably not. I mean, what is the center of a finite group? Probably has nothing to do with convergent. I don't even know what the Bend-Dixon theorem is. Bend-Dixon theorem. Dynamical system stuff, I see. I have no idea. Maybe in a topological group. Usually in any category theory, you can use any regular cardinal as your smallness bound. Alper's notes on stacks with triangles. Yeah, right. Although that also Daysen, that might not be. Well, I did bring that up. I'm not sure if that is exactly what you're after. But it is a very cool example, and you should check it out. Yeah. But I wonder. Yeah, like maybe I could be wrong, but maybe what you're after is something like a little more classical, right? Like you I look smoked. Do I? Let me I can't see myself right now on stream. Oh. I don't know. I didn't think so. But I'll take your word for it. I am not. Although the smoke is legal here in Canada. So I could be legally. But well, I did when I was a young lad, when I was a little baby boy, maybe not a little baby boy. I did hit the smoke. But now, I don't know. I'm just worried about my lungs and my lung health. I want to live forever. The coffee is not speaking for me. Oh, yeah? What do you say about that? Like we can treat the positive real numbers as sort of like the moduli space of circles centered at the origin, right? Because every circle centered at the origin is just entirely determined by its radius. So R is like a, right? It's just, can be identified with the set of all positive, right? So something like this, I guess, is nice. And then you could say, oh, well, if 2 points in the space are close together, then the circles will have like very similar, curvatures or radii or something, which is kind of cool. So maybe that's more what you're after. Or I remember once I was thinking about, and I know other people have done this before, but I was thinking, I was approaching this problem very naively in when I was in my master's. I remember dreaming about like the space of polynomials, and then thinking about, identifying this with, like, I guess we could just take C3 for the biggest case, right? So well, the space of all polynomials, of course, you can identify exactly with C3, right? Because of the coordinates. But then I was thinking that, well, then we also, within there, we have our discriminant, b squared minus 4ac. And then, we can basically like look at these algebraic, like basically look at whether this is positive, negative, or equal to 0, and that sort of breaks the space up into 3 pieces. And then the other thing I was sort of looking at is that I was like, well, actually, this is a homogeneous equation, and the discriminants are always homogeneous equations. So actually, one could then view this, because you could, right, so one could view this as actually giving us an equation in P2, complex projective plane, and then which also kind of makes sense, because I mean, maybe you really do want to consider 2 polynomials as actually different, but then it also seems reasonable that, like, well, maybe 2 polynomials where their scalars are just their coefficients are all scalar multiples by the same scalar, makes, those 2 shouldn't be different. So then you could collapse along that equivalence relation and look at this. This is not how far from moduli spaces are actually defined. Yeah. Like for elliptic curves, exactly. Yeah. I wonder, actually, if we go to a 3D graphing, let's find a 3D graphing calculator here. 3D graphing calculator. I want to see what this, okay, what would this equation look like? Right, so we'll call B, we'll go y squared minus 4ac equals 0. Yeah, so if we look at real polynomials, these are all the, whoa. Right, so I guess we can view this, like, if we thought about the, like, moduli space of all quadratic polynomials with real coefficients, this is the shape that would be made of all of those polynomials with discriminant 0. Right, so I guess make a video on some Langlands wonder all the way through, as to give an idea of what Langlands is about. I do have some Langlands videos up. I mean, all the way through depends what you mean by all the way through, because I mean that could take 400 years. I do have several Langlands videos. Let me go to my channel. I absolutely love these shorts. The Chit Show. I've been watching these shorts. I think they're hilarious. Yeah, I've got some Langlands videos. Go back in time. Make a video proving Langlands. Yeah, how about I do that for GL1 over a p-adic field? I could do that. Maybe. Langlands for commutative dummies, yeah. Right, so here's one video. That's only a 16-minute video, though. I did make a follow-up to that. That video is probably not that good, actually. Now I know so much more. And here's a not entirely wrong introduction to Langlands. That one's better. That one's slightly better. Actually, did I record a version? There was like a newer version of a Langlands talk I gave that was slightly less wrong than the other ones. I don't think I recorded that. Maybe I will, yeah, maybe I do need to make some more videos. Even for GL1, it's already class field theory, which can take a whole semester-long course. Yes, that's true, right. Yeah, maybe I should have said GL1 QP. I mean, even that is, yeah. I have not watched the new math-life balance video. No, I have not. I think this introduction to Langlands, is how you found the channel. Nice. Yeah, so maybe I should put a better introduction to Langlands video out there. Yeah. I should start thinking about it. But also there's a great there's a video series I was thinking of. I've been meaning to watch. I've watched some of these, but yeah, here, look, from wow, 2 years ago already. Jesus Christ, time is inevitable. Where's the full playlist? People mentioned Frobenius. Wow. Oh, AI is showing lots of cool stuff. Anyways, yeah, this is a whole series of lectures from my mathematical grandfather. You should go watch this. I mean, he already did it. Explanation of Langlands from beginning to end. You should go watch this. That's the move, I would say. What is this video with no views from an hour ago? That's only 2 minutes and 47 seconds long. It makes me think it's an AI video. But it also seems very interesting. Why do tennis serve speed stats vary between different tournaments? I'm intrigued. How has no one clicked on that an hour ago? Oh, tennis stat sheets. It's a whole channel dedicated to tennis stat sheets? That's kind of interesting. I feel like that's maybe a way for me to get into doing more statistics. There's interesting, there's interesting stats to be done in sports, I think. Yeah, I've never been crazy about, I've participated in various sports in my life. I've never been crazy about watching sports, but I feel like the road for me into both sports and statistics is maybe through sports statistics. Two things I could take or leave, but combine them together and I could really vibe with it. Yeah, how does lecture 23 only have 173 views? I mean, lecture 10 only is 449. People, that's what's wrong with the world. Kids these days, you guys want to... You have the greatest playlist. You have the greatest playlist on all of YouTube, and you guys are just here hanging out with me instead. That's your problem. How is hello Matthias? How is the funding in Canada? There might be a lot of competition for me there. I guess a lot of PhD people will be looking to work in Canada even more than before. Yep. Yep, that's true. Probably that competition from the States will bleed over. Um, yep. So, I guess we'll see. Funding's good. I heard some good news about funding recently. Basically, one of our funding programs, NSERC, has, I don't know, reorganized something. A professor here was telling me that they've reorganized things in such a way that should be good, should be an improvement for most people, and told me to, apply for the NSERC postdoc funding. So we'll see. I don't know. Maybe I'll just have to drop out and go make six figures instead, or not drop out, but I mean, you know what I mean. Abandon academia to go be rich. Wow, so this is the new goal: get more subs than the Fields Institute. That's an achievable goal. Do jet schemes have any other uses? So automatically, I don't know the answer to your question because I don't know what a jet scheme is. Besides giving strong-ish criteria for the non-singularity of varieties. Oh, thanks, Arad. Always saving me in chat. Ooh, in enumerative geometry. What the hell's a jet scheme, anyways? No, of course, yeah, I should have known. Yeah, don't jet spaces normally have to do with like infinite dimensional manifolds or something? For finite M, this is a version of the M jet space. It's a pre-sheaf. Thanks, NLab, for absolutely nothing. What about this? I guess what I just read should be an algebraic analog of this. Jet is an operation that takes a differentiable function, produces a polynomial. Oh. Okay. I don't know what's going on here. Oh, here's a jet space. Jet spaces from point to point. Roughly, a jet equals a higher order tangent vector. Okay, thank you, Arad. That was the one sentence I was looking for. You can see your week schedule until October for your uni program will be introductory statistics, introductory algebra, and real analysis 1 for the next 2 months until other things begin. Your weekly schedule until October is interesting. So your university dictates what you're taking, and you start now until October? Everywhere that does things differently than the specific way I did things is weird and strange. Well, maybe I will, maybe I'll have to check out that paper at some point. Although, I don't know. I don't know how deeply I'm going to dive into jet schemes. I'll be honest. I will be honest. You can say a linear operator is a differential operator of order k if and only if it factors through the k jet bundle. Interesting. That does seem interesting. Gets disappointed by looking at 173 views on Langland series. Also K, thank you for the one sentence definition. Yeah. I will be taking those courses October. It is first in the third year that you'll be choosing. First in the third year. I see. How would I define the use of algebra in university? I wouldn't. Yeah, I wouldn't. Yeah. But definitely not the same as algebra in high school. Well, the page that we're currently on, Mr. L, is the differential geometry perspective. Well, not entirely. We can already see here, but I mean, if something exists in differential geometry, you should suspect that the algebraic geometers have stolen it already. This isn't 100% true, but it's mostly true. So, yeah. But also, wait, why is this shaped this way? And what does that mean? But how would one do it? I mean, why would one do it? Why would one? I don't know. I guess maybe you want to explain. I guess maybe you want to explain to someone why. I guess you want to explain to someone why. What am I trying to say? Just what goes on in algebra in university. I don't know. I don't know how I would define it. Yeah, sorry. Oh, once your parents ask. Yeah, I don't know. I'm not sure what to say. Because it's a cube? Wait, what? What did I see? Because it's a cube? Where is a cube? Yeah, what's interesting here, though... what was I going to say about this? Oh, yeah, the other thing I was going to say is that it definitely aligns with our intuition, right? Because all polynomials take up, like, 3D space. And then we can see that those that have where the equation's set to 0... Oh, look, it spins on its own if I let it go. That's cool. But if it spins on its own, then... right, the polynomials take up like all of 3D space. We can see that this is just a two-dimensional sheet, though. So somehow that's like, that has measure 0, basically, in the space of all, basically has measure 0 in the space of all polynomials, which is kind of to be expected, right? Because, like, these are polynomials that have a double root. And there's just sort of one way to have a double. You pick the number that's going to be the double root. Whereas, polynomials 2 roots, you have 2 degrees of freedom. So, okay, this makes perfect sense that it would be like this. Right? The other sets will have, like, in fact, infinite measure, and so they both account somehow for the same amount of the full space of polynomials. Just gonna say math stuff? Yeah, I mean, yeah, I don't know. Your dad asked you once about algebraic topology. So you tried explaining, and his only follow-up was, is it related to AI? Yeah. 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 Just like we all do. No one ever actually answers what they actually do in math. Yeah. Yeah. I mean, my stock answer for I've been using, I don't know if you heard about this Time Left app. I went for dinner with a bunch of random strangers. And, yeah, I do have a little mini spiel where if they, I say, I'm in math, and then, most people, their eyes glaze over at that point. And then if their eyes don't glaze over and they're like, what, uh, do you, yeah, they ask a little more specifically, and then I say something about how I, try to classify symmetries. That's my go-to, which of course is a far cry from the Kasdan-Lustig hypothesis, but it's, a good, maybe a good enough approximation for dinner conversation. And then I explain something about how, a square, I grab something like my phone or a napkin. I'm like, well, the square has finitely many symmetries. And then, a glass, or something like this has, infinitely many symmetries. And then we try and talk about the differences between those. And then normally after that spiel, they're pretty cooked and they stop asking questions. Not that I want them to stop asking questions. I'd love to just explain all of Langlands to them right there on a napkin. But we all know that that's never going to happen. Yeah. Hello, Edit Smith. As a first gen, yes, I'm also first gen. Actually, that's not true. First gen grad student. My mother went to university. Actually, my dad did go to university as well, but he doesn't have a degree. But my mom does have a bachelor's. Not used to be able to explaining what you do since high school. Yeah. You think you have a geometric interpretation of the 3D graph? Modulo scalars. Ah, interesting. Well, yeah. I mean, modulo scalars. This part wouldn't change, right? I mean, this. You basically just lose half of this, right? They get identified. The discriminant is the square distance between the roots. So you're looking at pairs of roots with distance 0, right? It's easiest when it comes to anything a bit more advanced is to explain how to differentiate a disk from a circle using the fundamental group. What? You think that's the easiest? I mean, I guess. But also, I wouldn't... Yeah, I mean, sure. I don't know. I wouldn't say that that's the easiest. I would not say that that's the easiest. A. And B, I feel like, the story that I cook up for people should be an approximation to my research. And that doesn't feel so much like an approximation to my research. Sometimes you just have to accept they're just small talking. Yeah, and not actually that interested. Yes, exactly. Yeah. But then it's hard to gauge, because there was one time, I mean, this is an incredibly rare scenario. Probably the most of the time people are just, they're like, oh, okay, you're a mathematician, and that's all they care about. Why did you get permanently banned from R Math? What did you do? But give us the juicy gossip here, Edit Smith. But yeah, there was one time I was at some social thing, and there was this woman who was asking about what I did. And I mean, it's interesting because I've sort of been trained to not say too much, precisely because of this reason, because people mostly just want small talk and they don't actually care about whatever it is. And then, but she seemed sort of annoyed that I was not. She was like, oh, but what do you do? What do you study? And I was like, well, I kind of study symmetries. And I guess she wanted more of a concrete answer, but then I don't know, but after I realized this and before, Literally just for being conservative? Okay, well, that's not true. That's not true, Edith Smith. Um, I'd be interested to see your post. I'd like to see the screenshot of your post, because absolutely that's not true. And now I'm really curious as to what you actually said. So if you want to email me a screenshot of what you actually said, I'm very curious. Would I say I believe in types? Depends what you mean by that. Because in Langlands, a type of a p-adic group is a compact open subgroup with a special kind of irreducible representation of that compact open subgroup. So, in that case, I don't know. More likely, you mean type theory, which, by the way, I have a whole video on homotopy type theory, about when I went to Italy to for a couple weeks to study homotopy type theory. So yeah, type theory is awesome and cool, especially when it gets to homotopy type theory. So, have I ever gone down the game of life rabbit hole? I don't know about the rabbit hole, but I've certainly sometimes at the beginning of class I show my students cool math things, and I've definitely shown them videos of the game of life. How much of a competitive environment is the study of math in university? Are there full-on snobs? They're pretending to be super intelligent and not really that curious. I don't know. Like, it's kind of hard to bullshit in math, but that's not actually, I mean, I don't know. Maybe at grad school level, no. Well, I guess there are snobs. I don't know. I mean, I'm at, I don't even know if my university's top 50 or even top 100 worldwide, to be honest. I don't know. I'd have to look it up. But, so, I don't know how universal my experience is. Definitely, I've certainly met undergrads, and maybe I've even been guilty of this in my time when I was younger. People talking about things they don't actually understand, and just saying wrong stuff. And then other undergrads are like really impressed by them because they're like, whoa, he's talking about cohomology. And then they think that person's really smart, but they don't actually know what they're talking about. Certainly that happens. Yeah. But I mean, I don't know. It can be, it's pretty easy to expose someone mathematically when they don't know what they're talking about. So I don't know. I don't think it's that bad. How competitive is it? I mean, I don't know. Probably more competitive at more prestigious institutions, I would guess. Yeah, but I don't feel like it's competitive. Like, I'm working on my work and other people are working on their work. You know what I mean? You actually got interested in math as a teen when you stumbled across NLab. Wow. Wow, that is a very interesting arc. That's a very interesting way to get into it. Not a stupid question at all. Yes, I am a tutor. I accept tutoring students. I've got like 2 regulars now, about to have 3 regulars. I might have to cap it at 4 because of the amount of time that would take, but maybe not. Maybe I could take 5 or 6. Depends how many times a week I meet with people. Easiest when it comes to course I've taken recently or taken, right. Trying to explain italical homology, yeah, as opposed to those, right. Yeah, you can't explain those to anyone. Here's some gossip. Your cousin asked you to go to the casino when he found out you're studying math. Right. Yeah. Um, yeah. Although, I mean, that's not so crazy, right? Because, I don't know. I mean, card counting is interesting. You probably could. I mean, anyone can learn how to count cards. But what's so interesting about homotopy type theory? Go watch my video. Go watch my video called Hot Boy Summer. Yes, yes, Darius. I mean the Hot Boy Summer one. Go watch that. I talk about why I think it's so cool. There's some parts in there where I just talk about me traveling around Italy. Yeah, skip those. It's got timestamps. You can just skip those parts. But go watch that video. The ego gets killed almost instantly in real analysis. Yeah. I mean, it is interesting. It is interesting. Being a grad student, you interact with undergrads in interesting ways because you take on like a mentorship role, and then, but there's also, so you develop personal and mathematical relationships with undergrads, but then you also grade their exams, and so you see how some of them talk and interact with each other. And then you see when the chips are down how they actually perform behind the scenes. So I'll just say it's interesting to compare and contrast those things. Do I know the proof of why induction works? Is by Pascal. Well, is Pascal's the mathematical proof? I can't think of it right now, but well, I don't know. I think probably. I mean, I guess I think we proved it actually. I think we proved it in my set theory course, by which I mean like we started from the axioms of ZFC and built up all of set theory, including constructing the operations of addition and multiplication using the like recursion, which took like forever to prove, and then after using recursion and doing a whole bunch of work there, then we prove things about arithmetic. Knowing math should get you to not go to a casino. That's true, actually. I mean, that's why I don't like, I never gamble or buy stuff. Well, that's not entirely true though, Arad. I mean, it should, knowing math means you should not play games of chance. Or games that are purely games of chance. But I mean, like, it's well known that so yes. Generally speaking, knowing math should mean that you don't buy lottery tickets and that you don't go to a casino. However, that being said, there are also there are known ways, there are very famous stories of people breaking the casino because of their knowledge of math, including counting cards, right? I mean, it is the knowledge of math and the knowledge of statistics that allows you to say, oh, okay, well, if I have such and such capital going in, and I know that if I count accurately, then I can have this statistical edge, and then therefore, over time I can, on average, I will accrue wealth. Okay, I'm gonna go soon. It's late in the day. I gotta do some work. Knowing math. Oh yeah, I read that. Have I taken some courses by Schulze? No, I have not. I've looked over some PDFs. Oh, you were asking Nicholas because he's up on. Right, I see. It uses well ordering. Well ordering to prove induction? Probably. I don't remember, probably. Sounds like sociology. I mean, hey, that's part of it. I mean, some games, right? Some games Texas Hold'em definitely involves psychology, sociology, and a little bit of math. Blackjack is mostly just math, but yeah. Go make my advisor proud. Yeah, exactly. That's time to go crunch some proofs, yo. Okay, go prove some stuff. We'll talk about more random nonsense. Not tomorrow. I'm climbing mountains tomorrow. Leaving early in the morning. So, yep. I'll see you guys probably on Monday, though.